Point two, the mass balance models are written as areal concentrations. Normally in a mass balance model you have V times dc dt, right? The volume times the concentration change, which is kilograms per day. Well, if you divide through by the cross-sectional area everywhere, then what's left is the depth. And this now, instead of being a concentration, has the units of a flux. Grams, see, it would be normally grams per meter cubed, right? And if you divide it by the area, you end up with grams per meter squared. So and the reason we do that is because we're thinking areal dependency. So the lake models are all built like this because everybody's thinking the vertical dimension is the most important, but it's just a convention. And the fraction, so the model looks like this. The fraction, the POC of the ith G1 and G2. G3 is conservative in the original formulation. So this is the fraction of POC that's in either G1 or G2. Whoops. This is the rate at which it is being decayed away, which I'll show you in a minute. Why does it do this? I use a mouse. I don't use these touch pads, which are designed for. There is then loss by burial. I'll show you exactly how that works. And this is the mineralization rate. This is the 3.5% a day, or 0.1% per day. That's the correction factor for temperature, and there's POC. I think that's everything. So how do you do burial? Well, the way burial works in a sediment is things don't bury. What happens is material gets deposited at the top, and then the depth of the sediment changes, right? Let's imagine that this is bedrock. So over a period of time, from T1 to T2, there's a certain amount of material that gets deposited. So the way we do it is we attach the coordinate system to the top of the sediment and keep the sediment depth constant. And so the amount that accumulates there squirts out the bottom. And so the idea, and it's a completely mixed volume, we don't have stratification, so the amount of material that gets deposited pushes a certain amount out the bottom. So where's the idea that you have a fixed depth of mixing? And that comes from bioturbation and the action of essentially organisms that mix sediments. And we'll get to that a little bit later. So in your head, you should imagine the following thing. There is a layer of 5 to 10 centimeters. 10 centimeters, I think we use in the bay? Yep. 10 centimeters. And that number is fixed. And that is basically the depth over which material is homogenized. When you see very nice sediment cores, where you see nice gradients and whatnot, they go find places that are anaerobic and everything's dead. And then you get a very nice gradient of everything. But in the most of the bay, it's all just churned up. The top 10 centimeters are well mixed. Clear? So, yeah.
Just a
sure.
question. If I understand it, that the burial rate is kind of determined by the sedimentation rate.
Correct.
Okay.
Yeah, of everything. Of all the material that settles, exactly. Yep. And so to determine what that is, you have to get a way of measuring what the sedimentation rate is. Okay? All right. So you have a model which computes the rate of change of POC with respect to time. And what I want to know is what is the rate of diagenesis? And what that means is, what is the rate at which the stuff is being mineralized by that term? So POC can only go, or PON or POP, can only go three places. Well, first you have a source. That's coming in from the water column, right? That's being deposited. If you don't bury it, well, then it's being mineralized somehow. So we call the flux, the mineralization flux, or the rate of diagenesis. Diagenesis is fancy talk for mineralization. I didn't invent any of this, by the way. It's all the geochemists. And if you add up the amount of material that's G1 and G2, then the total amount of diagenesis of carbon material that is being mineralized is J sub C. So that's an important variable that we think about. So that's grams per meter squared per day of organic matter that's turned into soluble something or others. Okay, so it's either acids or it's whatever, but it's being mineralized, okay? And then we have to track that mineralization through the reactions. So if you solve the steady state equation for G1 and G2, you end up with that the POC for 1 and 2 is the fraction divided by the two loss terms. Either it's buried or it's reacted. And for G3, there is no reaction, so it's all burial. Clear? So, is it burial or is it mineralization? Well, if you take a look at what kinds of burial rates are out there, you find in the ocean it's millimeters to tenths of millimeters. In bays, it's, you know, it's a tenth of a millimeter, it's a millimeter to, I'm sorry, a tenth of a millimeter to a centimeter per year. And the high deposition rates, it's 1 to 2, maybe 5 centimeters a year. That's a very high deposition rate. We have the reaction rates, and so what you end up with is that for G1 and G2, diagenesis is very much larger than burial. You don't ever lose any reactive material by burial. It's all reacted away long before it's buried. So next point, all organic material that's deposited comes back unless you make something that doesn't react anymore, which you can then bury. But if it all stays soluble, that's what it's telling you. All right? Well, all of it is being turned into diagenesis flux. What happens to the diagenesis flux comes later in the story. So burial is only important for solid material and for G3. Next, can you measure the rate of mineralization? How many of these experiments, Jim, have we done over the years that never told us anything?
Well, you got Burdage,
Yeah.
also the recent work that
Jeff Cornwell did? Yeah.
In the Bay.
Yeah.
Conowingo, rather.
Right. So the way the way Dave Burdage did these experiments, 1991, which he did at ARC, by the way, we decided we needed them. So the way he did it was he mixed 3 times, the water to sediment ratio was 3 waters to 1 sediment, so it's a very thick slurry. Put them into test tubes and just kept them at whatever the temperature this thing was run at from 4 different stations in Chesapeake Bay, and then would pull a test tube at every time. So these were not continuous reactors. These were individual sealed tubes. And measured the sulfate in time, measured the carbon dioxide being produced in time, measured the ammonia flux, and measured the phosphate. And up here are the curves for ammonia, if you consider it conservative, that you'd see for G1, and then that line would be G1 plus G2. And you can sort of see you see the way it starts off fast and then flattens out. You can see it down here. See, it starts off steep and then it flattens out. So you can get 2 things out of this. One, you can get a rate. You're not quite sure why it's different among the different stations and so on. We were never very successful. I don't know what Cornwell's results told you, if they ever...
The only thing that we really got out of Jeff's experiments were ammonia production, because perhaps a little bit of the way Jeff set it up, the amount of phosphate that was being produced because of the high iron
yeah, it was all being...
was all partitioning onto the
Yep.
solid, so there wasn't much of a change.
Yep.
And something went wrong with the CO2 at the end, that whether it was a capsule or leakage, but the rates at the end, we ended up getting negative rates for most of the,
Really?
the carbon.
That's too bad.
So the only thing that really worked out, and even that was a little bit questionable, was the ammonia data.
Yeah. So this data was a little hard to deal with because we didn't understand the difference in the rates. But what we could figure out was what the stoichiometric ratios looked like. So if you go back to the data, in the first, I can get the delta the delta sulfate from that difference, and I can get the delta ammonia from that. These are anaerobic production, by the way, right? No oxidation, so these are all anaerobic seals. So by taking delta sulfate and delta ammonia, or delta carbon dioxide and delta ammonia, I can get the ratio of the 2 fluxes, the diagenetically produced fluxes. And remarkably, the carbon to sulfate and the carbon to sulfate's right on the nose. So Redfield stoichiometry is basically CH2O. It's glucose, C6H12O6. So that organic matter stoichiometry, you don't get better. So that assumption's terrific. The Redfield assumption, unless you look hard, and there's a paper that Francois Morel did many years later where he looked really hard and found some places where it wasn't quite right. But pretty much, as you mineralize these things, so sulfate to carbon is exactly what Redfield says it is. This, by the way, is assuming that the sulfate goes to sulfide. It's a complete oxidation. The carbon to ammonia ratio is a little different. You see that the shallow segments are slightly higher in nitrogen ammonia relative to the CO2 flux, and the deeper ones are slightly less. The nitrogen species in organic matter mineralize slightly faster. The proteins are a bit more labile anaerobically than the cellulose and the starchy organic matter. And that's the difference. But still, it isn't a terrific difference, as you can see. The thing completely falls apart for phosphorus. The ratios are all over the place. And as Jim pointed out, we think that's because of phosphorus and iron partitioning, which we'll get to a little later in the talk. Clear? So stoichiometry looks Redfield. For ammonia, for organic matter, it looks pretty Redfield-ish for ammonia carbon and not at all for phosphorus. So,
I'm sorry.
Yeah,
it
shoot.
Could be, and it could be just as you said, the partitioning is what's
yeah.
driving the differences.
Oh, absolutely.
Right.
Absolutely. It's exactly that. This is soluble phosphorus. This is not total phosphorus, because otherwise you'd have to measure inorganic phosphorus. Then presumably that would work. Yeah, that would work if you did an inorganic extraction.
As long as you got your initial condition.
Right.
Blah, blah, blah.
Yep,
Right.
yep. So ammonia is the easiest one to model because it has more or less the simplest reaction kinetics, and so that's the one we started with, and it's instructive. So here's how the model is built. 2 layers, H1 and H2, exchange with the overlying water, and there's a surface mass transfer coefficient. K, the notation is K sub L. That's the conventional notation for a surface mass transfer from layer 0 to layer 1. So when you see KL01, it means from layer 0, which is the overlying water, to layer 1. Diagenesis in the aerobic layer, JN1. Reaction, nitrification in the aerobic layer. Diffusion between layer 1 and layer 2. Diagenesis in layer 2. We actually then put these, well, you'll see. And there's no reactions. We assume that once you make ammonia in the anaerobic layer, it just stays put. Okay? So, mass balance equations. Rate of change of ammonia in layer 1 minus the first order reaction rate of nitrification. Damn thing.
Hey, Dom, do you want to borrow my mouse and plug it in and use a mouse?
I would love that. That would be wonderful. I live with mice. I don't live with touchpads.
I try and kill them in the house.
Thank you. Well, it even talks to me. Do I have to turn it on?
I think it is. Yeah.
Wonderful. Merci beaucoup. I can use the little rotor. Right, so rate of change of interstitial water ammonia in the aerobic layer minus the nitrification rate, minus the transfer between the sign, by the way. The way to get the sign right is that the self term, the ammonia term, has to have a negative sign. So just to make sure you got it right, just make sure that that thing ends up with a negative sign. So this is the transfer between 0 and 1. This is the transfer between 1 and 2, and you see that that also has a negative sign. So these are the losses by mass transfer out. This is the source of diagenesis. In the anaerobic layer, you just have the transfer up and the production by mineralization. That's all of that. If you add the two equations together and set the derivatives to 0, the internal transfer subtracts out, which is a cute trick. You see that this thing's got a positive sign there and a negative sign there. So if you add the two together, it subtracts out. Because, of course, what you're doing then is you're modeling the ammonia in the whole system. And you end up with that, which you can then solve for the concentration of ammonia in the aerobic layer and the concentration of ammonia in the anaerobic layer. So let's first calculate what the flux looks like. So the flux has got to be the surface mass transfer coefficient times the difference between the overlying water and layer 1 ammonia. And if you do that, you get this very nice, neat formula. So the ammonia flux that comes out is equal to the amount of ammonia that's generated by diagenesis times the ratio of the surface mass transfer coefficient over the surface mass transfer coefficient times the first order nitrification rate times the depth of the aerobic layer. So let's see if that makes sense. If the surface mass transfer coefficient is large relative to that, this thing ends up being 1, and the ammonia flux, and let's neglect that for a minute, the ammonia flux is equal to the ammonia diagenesis rate, right? Amount produced is the amount that squirts out. On the other hand, if this mass transfer coefficient is real small, or this thing is real large, large, then this number dominates, and you get a big number in the denominator, and now the ammonia flux is a good deal less than the ammonia diagenesis. So it's simply a competition between how much is exchanged to the overlying water and how much is nitrified. Yes? This one's a little more interesting. The overlying water produces a negative flux, of course, into the sediment, right? And its magnitude depends on the reciprocal of the sums of reciprocals. You'll see that formula in a lot of the equations in the model. And the reason is that, so let's think about how it works. Suppose the surface mass transfer coefficient is large. This number is small, but the reciprocal of a small number is large, and so you're getting a lot of transfer. So it is the reciprocals of these things that are weighed, not themselves. Isn't that interesting? So go think your way through that. Convince yourself that that's right. Also, take a look at this. You notice that the ammonia flux does not depend on the concentration of internal ammonia concentrations. Right? It is not true that the ammonia, you can write the ammonia flux, of course, as, I need two hands. You can write the ammonia flux as the difference in the internal, using the internal concentration, but once you make the substitution, what you find out is that the flux is determined entirely by diagenesis and the transfer and reaction rates. These things result from how big the source is. If I double the diagenesis rate, this thing changes, this thing doubles, and the flux changes by this much. It isn't, so the causation is not that pore water concentrations cause fluxes, it is that the rate of mineralization causes fluxes. And that's just what I said. And JN1 is the source from, JN is the source from layer 1 and layer 2 when you add them together. Okay. But the tricky part is, what's the surface mass transfer coefficient? I need to know that number because it's half of the answer. Equivalently, I also need to know the depth of the aerobic layer. So I've got a problem right away. I need to know that. And the trick, the idea that we used for this, it's actually an idea that other people had as well. We found out later. But anyway, imagine what the profile looks like for oxygen in the overlying water, oxygen in the aerobic layer, and oxygen in the anaerobic layer.